so we're virtual. So yes, I'm going to talk to you guys about, if I can make my screen advance, about the U.S.Argo Data Assembly Center, or DAC, which is housed here at AOML. And then I'm going to delve into a few of our Argo data uses. All right, so the Argo program is an international program that works to understand the ocean to improve ocean and weather forecasts. These are resident autonomous robotic systems. So our Argo floats are deployed from ships, and they sink to a drifting depth of typically about 1,000 meters. Interestingly, if we deploy in the loop current, which I've recently learned from Jen, because I don't deploy floats, recently learned that these floats need to be deployed to a drifting depth of 1,500 meters. Otherwise, they get washed away by the loop current. So that was very cool. So these floats sit at the drifting depth for about 10 days, before they descend to their profiling depth of around 2,000 to 6,000 meters, which depends on their float type. Once they reach their profiling depth, they turn around and they rise and measure the water column all the way to the surface as they ascend. Once they reach the surface, they transmit their data via satellites to our home bases before starting the cycle again. So with these cycles, we're not only measuring the essential ocean variables throughout the water column, but we're also able to interpret what the currents are doing at 1,000 meters from that drift cycle. All right, so as I mentioned, the Argo program is an international program. So here's a snapshot of just the float deployers and operators for July 2025, and you can see many countries are involved. All right, I'm going to walk you through very briefly through how the data pass through our full international Argo program. So our Argo floats transmit their data from the float to one of many data assembly centers, or DACs, which here at AOML, we house the U.S.Argo Data Assembly Center. So we are responsible, we're one of many DACs, but here we're responsible for all U.S.Argo data. So within the data assembly centers, we quality control the real-time data, and then we create buffer files, which we then send to the GTS, or we create NetCDF files, which we send to two what we call global data assembly centers, or GDACs. So one is housed here in the US at NRL Monterey, and the other one is housed in France at Ephrema-Coriolis. So at the GDACs, they perform a few more data checks, or rather file checks, to make sure the files are in the formats that we need before they're transmitted out to the users. There is the GDACs, both GDACs mirror each other, so they should be identical. And we do take a snapshot of the global data assembly data sets once a month, which are then stored at NOAA NCEI. So what I want to highlight in this slide is this feedback loop that goes up and down between all of the different groups. So we at the within the Argo program communicate really well with each other. We work continually together to make sure that what data goes through our system are the best that we can produce. So there's feedback from the users, feedback from the float manufacturers, feedback between the DACs and the GDACs. We're all continually working together to make sure that we provide the best available data. All right, so as I mentioned, here at AOML, we house the U.S.Argo Data Assembly Center, and we process and quality control all U.S.Argo real-time data. So as of July 2025, that means that in our US database, we contain 1.8 million U.S.Argo profile files. And that comes from 9,000 floats, of which 2,000 are currently active. We're able to transmit our data from the float to our users in about 2 to 3 median hours. Okay, so we do have different float types. We have core floats, which measure temperature and salinity to a depth of 2,000 meters. And we currently have about 1.7 million profiles in our US database. We also have biogeochemical floats, or BGC floats, which measure the core parameters, as well as chlorophyll A, fluorescence, oxygen, nitrate, pH, and backscatter, down to 2,000 meters. And we currently have about 127,000 of these BGC profiles in our US database. We also have deep floats, which, as you can guess, measure deeper than the normal floats. So they can go to 4,000 to 6,000 meters. And we have about 36,000 of those profiles in our US database. And recently, the ARGO program has been focusing on deploying floats in the polar regions so that we can investigate the waters under the ice. And we currently have about 53,000 of those polar profiles within our US database. So here at the DAC, we produce monthly metric reports that give you an overview of our operations every single month. So I've thrown a number of numbers at you, excuse the pun, a lot of numbers at you. So if anyone wants to know what these numbers are every single month, please feel free to either sign up for our monthly metric report or look on our AOML Argo operations website and you'll find them, all of the reports there. So this is where I'd normally show you a snapshot of all of our U.S.Argo floats over a single time period in a day. But AOML has recently produced this incredible video. It's on YouTube. It shows our observational reach in the year 2024. So instead of showing you that snapshot, I'm going to share this little video with you just to broadcast this because I think it's fantastic. If you are looking for Argo floats, you are looking for these little red dots. And as you can see, we have a global footprint. But again, this just showcases what AOML touches in 1 year, which is fantastic. So go and look on YouTube. All right. So whose floats are we processing here at the U.S.Argo DAC? So in the US, we have a group called the U.S.Argo Consortium. And that is made up of a number of groups from AOML, PMEL, Scripps, the University of Washington, Woods Hole, and the NRL. So the majority of the floats that we process, and here you're seeing the annual count of float profiles per year, you can see the majority is from the consortium. However, we also process from other agencies that I'm showing you here. Saying that, we work really closely with our private industry partners because they're the ones that are able to make sure that we understand the instrumentations that they're using. So between the float deployers and the PIs who own the floats, the manufacturers, and our data assembly centers, we have a really high level of communication to make sure that we're producing the best data we possibly can within our US AOML DAC. So our data set in the US is made up of 87% core floats, profiles, 8% BGC profiles, 3% polar, and 2% deep. And these data have been collected over the last 25 years because the ARGO program has just turned 25, and we were recently dubbed the crown jewel of ocean observing systems. So I wanted to introduce you to the DAC. These are the DAC team members that have literally processed over 87,000 profiles each year for the last number of years. One thing I wanted to highlight in this slide is that I am the only federal person that works in our U.S.Argo DAC. The rest of the team are all CIs from the University of Miami CMIS team. Okay, getting into the nitty-gritty of what we do. Here is a bird's eye view of our processing protocols within our U.S.Argo DAC. So I'm not going to dive too much, but I do want you to know that we're able to process 64 different formats from 10 different floats and 5 different manufacturers. And I've got a +1 there because we're working with another manufacturer right now. We are a hybrid redundant system here at AOML. So we not only do we run our processes on-site, in-house, using our own servers here at AOML, but we also have a backup redundant system in the cloud at Amazon Web Services. These are mirrors of each other. They're maintained daily, so we can turn them on, turn them off, and switch between the two intermittently, no problem. At the DAC, we mainly work on the real-time data. That is our bread and butter. So all of these systems that all of these float data have to pass through are automated using AI and machine learning techniques. As per all data sets, you can automate as much as you like, and about 90% of our data get through. But it's that 10% that we have to manually go and deal with. So no matter what we do, we will always need folks on hand to work on that 10% of data. A float doesn't transmit its full transmission, so we have to go and patch it with another float. And as much as you try and automate that, it always needs manual intervention. So that is how our real-time data flow runs through our system. We also take care of the delayed mode data transmission. So within the ARGO program, we rely on our PIs who deploy the floats and who are experts in their region of interest to delay mode their data. They know what they're looking at. They are experts in every single piece of water that they deal with. So we rely on them to do their delayed mode QC. However, they then pass their files to us, and we transmit it to all the different agencies. And as I mentioned, we're able to transmit our real-time data within 2 to 3 hours from the float to our users. And our users are, as I mentioned, the GTS and Coriolis, which is one of our GDACs, as well as our Navy GDAC. So our 2 global data assembly centers. Okay, so now I'm going to tell you about a new thing we implemented this year, which is our U.S.Argo DAC ticketing system. Taking a step back, the Argo program is a heavily regulated and highly controlled program. And these implementations are created, or rather, the folks that are driving our monitoring is the International Argo Steering Team and the Argo Data Management Team. These are the folks that set all of our restrictions on what we can do with our data. They set all of the protocols. And what I'm showing you here is a snapshot of what we call cookbooks. So anytime there's a new float, a new sensor, a new protocol for quality controlling the data, and this is international, so all of the international teams work on this. Anytime anything is changed in how we handle the data, these cookbooks are updated. So we are constantly updating our protocols and techniques to make sure that we are providing the best available data to the community. So that means we have a number of code edits daily. So since 2017, we've had over 1,000 code edits here at the DAC. Half of those are BGC at the moment and half are core. So with our active floats, half are core, half are BGC. Previously, we tracked these code edits with a spreadsheet, and they equated to about 11.5 tickets a month. However, since we've implemented our new AOML U.S.Argo GitHub ticketing system, we have it's been really heavily adopted by our community, which is so fantastic. And our ticket rate has upped itself to 45 tickets a month. And that is absolutely super, because that means that we're catching not just the code, thanks Vanellas, not just the code changes, but we're catching all of the U.S.Argo DAC requests we get. So that's anytime a float needs to be processed, anytime a file needs to be replaced, a delayed mode file needs to be replaced on the GitHub. So all of these extra changes that no one was capturing before and all these requests that we had are now being captured by this ticketing system, which has been so good for our transparency as a DAC. That means anyone in the consortium can see what we're working on, can see who else is worried about. So if one agency is asking us to do this and another agency think, oh, that's a great idea, now they can see what everybody's asking us to do. So our transparency and our communication across the consortium has really increased with this. We've also offered this ticketing system to the consortium so they can use it for cross-academia and private industry purposes too. Okay, so now I'm going to tell you about some new data dissemination uses. The current US Global Data Assembly Center, or GDAC, is run by NRL Monterey, and they will not be able to sustain that system for much longer. So NCI has kindly offered to step up, and they are working on their own Global Data Assembly Center. So we have become the first Argo DAC to transmit data to this prototype NCI GDAC. And that makes sense because using us as a test bed is wise. We are the largest DAC across the globe. We handle the most amount of data. However, we are still sending to NRL and the French GDAC, so there is no break in transmission as per usual status. And as a lot of you know, we are transitioning from the GTS to the new WIS 2.0 system. And we are the first global Argo DAC to adopt the new WIS 2.0 native cloud data distribution system. So we are currently sending our buffer files to both the legacy GTS and the WIS 2.0 system, which means, again, no break in service to our clients. We are just disseminating to both systems. Okay, now I'm going to switch over to some Argo data uses. because it's all great if you guys know how we do it. Now you need to know what we're using them for. ARGO data are the dominant source of global subsurface ocean data. They are used for ocean and weather forecasts, changes in long-term weather patterns, global rainfall, global ice volume, and sea level changes. In fact, I believe that ARGO data, we have 4 times more ARGO data than any other subsurface data set combined. I love showing this plot. So this really highlights the importance of the ARGO data when you can see the reduction in uncertainty around the ocean heat content after the inception of the ARGO program. Our ARGO data are used in over 600 NOAA products to meet NOAA strategic goals. And this is the 2024 count. We're still working on the 25 count, but our ARGO data were used in almost 7,000 papers. As I mentioned, our ARGO data are essential for long and short-term weather and ocean forecasting. They're used for extreme to interannual weather events. Here you can see these are all the Hui floats that happen to be near these hurricanes. They're used in search and rescue operations, fisheries management and monitoring, oil and gas industry, maritime safety and navigation, and in military applications. And here is such a great little schematic that tries to capture all of our operational uses. So I'm not going to step through this, but if anyone wants a copy, it's in our monthly metric report. I'm going to get you to sign up if it's the last thing I do. So this year we did an exercise where we tried to capture all of the U.S.Argo operational data uses within our federal agencies. And as you can see, the mind map got a little convoluted, so I'm not going to expect anyone to try and read this because not a chance. But if you're interested to see how NASA or the USDA or the National Ice Center or the FAA or oil and gas industry use our ARGO data, you can guess. The link is in our monthly metric report, but you always can email me and I'll send you the link. All right, what do ARGO data tell us? ARGO data are heavily used by our modeling communities. They're used for forecasting, for model initial setup and validations, reanalysis and state estimation, for understanding ocean processes, ocean variability, teleconnections and extremes, to guide and assess developing versions of forecast systems prior to operation, planning explorations, and assessing the feasibility of operations at sea. As I already gave you a sneak peek, they're used for ocean heat content because we have really high quality sensors with global and temporal coverage down to a depth of 6,000 meters. In fact, the ARGO data set is one of the best data sets because we have a minimal spatial and temporal bias. Our floats don't rely on heavily trafficked shipping lanes or can only measure during summer seasons because the winter conditions are too harsh to measure the conditions. Globally, we have 3 million core profiles. So we can use these data to look at year-to-year and fluctuations and long-term trends in ocean heat content, which is what Hui has done. Here is a plot showing the global average ocean temperature anomaly, and you can clearly see the ENSO signal in the top 600 meters with a consistent warming trend at depth. And many thanks to Scott Glenn from Rutgers, who allows me to use his slides where he uses ARGO data, which you can see as these points underneath Hurricane Idalia in 2023, to look at the RTOPS ocean heat content. And here again, he's using the same ARGO data in RTOPS to look at Helene in 2024. Obviously not the same ARGO data, still ARGO data. All right, so ARGO floats, as I mentioned, are used to track the global water cycle, so we can track patterns and balance of evaporation and precipitation, both locally and regionally, and we can predict increased drought in arid areas and flooding in wet areas, which is what Hui has done here. So here you're looking at monthly and interannual anomaly ARGO salinity data, and you can see a distinct increase in salinity in salty areas and a decrease in salinity in fresh areas. And again, Scott gave me a great slide to use where you can see how they've used the Argo data in their RTOPS model to look at salinity under Idalia in 2023 and Helene in 2024. Okay, Argo are also used to look at steric sea level. So sea surface height is dominated by changes in subsurface density. Our Argo floats measure temperature and salinity as a function of depth, and we can tell how much of the sea surface variability is steric in origin. We can also look at how the steric signal is distributed over depth and between the salinity and temperature. So when you combine that with altimetry data, you can resolve basin scale signals on interannual and decadal timescales, which is what's been done. Argo and JASON and the Satellite Gravity Recovery and Climate Experiment, or GRACE, those data were used to partition global sea level rise into steric and mass-related components. So here, and this is the plot from the yearly state of the climate, where you're looking at global ocean mass from GRACE and the GRACE follow-on experiment in blue, with our Argo mean steric sea level in red. When you add those together, you get the purple signal, which very clearly mirrors the global mean sea level measurement levels that we got from the NOAA altimeters. So here you can clearly see how Argo is used to isolate that steric sea level. Of course, Argo floats are used for ocean currents and circulation. So our trajectory data are used to calculate deep displacements and current velocities. In fact, that's what Zhang et al. Did, where they used Argo data to look at the performance of the global HICOM flow fields. Here you can see where they've overlaid the Argo trajectories on their subsurface flow fields. And then they calculated the deviation between the real and the simulated Argo profile sea surface trajectories. And they came up with the conclusion that HICOM generally conforms to the basic characteristics and trends of the ocean current, but surface deviations increase with increasing latitude, and subsurface flows exhibit regional differences, with the largest differences being in the Gulf Stream, North Atlantic warm current, and westerly wind drift region. All right, so how are we using BGC data? Well, here's an example where folks have used the BGC data to unlock the global seasonal cycles. And we have over 350,000 global BGC profiles to use. So I came across this video the other day, and it was such a great video. I'm going to share some of it with you.
Just like land, the ocean has seasons. Seasons when things grow, and seasons when things decay. We know this thanks to hundreds of robotic floats equipped with oxygen sensors, collecting data about ocean health and transmitting it back to scientists on shore. These floats are part of an international research program called Argo. Each circle is one float. The color represents the percent oxygen saturation, an indicator of microscopic plant growth and decay. When the circle is green, it means microscopic plants are growing and releasing oxygen into the water. When the circle is brown, it means the tiny ocean plants are decaying and using up the oxygen around them. This seasonal cycle is just like when flowers bloom in the spring and trees drop their leaves in the fall.
I just couldn't resist showing that to you guys, because that was such a great little example of how they're using BGC data. All right, of course, we have polar data now. We have 52,000 US polar profiles. And these can be used, for example, to look at the extent of sea ice in the Antarctic. And if anyone knows me, my father is a retired ship captain who spent the last 17 years of his career in the Antarctic on the S.A. Agulhas and the S.A. Agulhas too. So seeing how our Argo data are being used for literally real-term ideas like that is fantastic. Okay, so I'm going to touch on a few of our operational centers that use Argo data. And I purposely bombard you with all of this list because these are just the systems that are just linked to Ocean Predict. So our Argo data are ingested by Ocean Predict community, and these are the systems that use it just through that. Some other systems that are using our Argo floats through Ocean Predict for forecasts and analyses are listed here. And I wanted to point out the bottom one, the North American Multimodal Assembler. That's actually housed at the University of Miami across the street from us. And here they're showing how they used the NMME model to forecast precipitation for September to November 2023. And I'm highlighting it even more specifically because one of the principal investigators of this program, or this modeling system, I should say, is also the director of our CMIS team. So that means all of those folks that you saw earlier in our DAC team, that's their boss. And I thought that was a cool little link to share with you. All right, Argo floats and hurricanes, topic of the moment. Again, Scott really kindly shared the slide with me to showcase the hurricane model forecast suite that they use at EMC. And of course, ocean data, not just Argo floats, but everything is heavily used within this modeling suite. And I really wanted to show you guys how Scott used our Argo floats to investigate the intensification of Hurricane Idalia. So first of all, when the float was, the hurricane was forming, they were using HF radar to watch the hurricane. Then as it intensified to Cat 1, they started using the Argo floats that were available in the area, which you can see right here. Oh, wrong way. Then as it intensified to a Cat 2, they were able to use the Argo floats and gliders that were now in the area. And then finally, when the hurricane reached the shelf, we can no longer access Argo data because Argo data cannot sit in the shelf. So they used hurricane gliders, sail drones, and HF radar. And here's a great little graphic that he shared with me where they were able to use the HAPS forecast system to look at the forecast winds, to forecast the wind speed on top of those two Argo floats that were in the area. All right, hot off the presses. Thank you to Lev for bringing this to my attention yesterday. So what you're looking at here is today's simulated or proposed track of Tropical Storm Erin. And Lev gave me this great graphic of what he's done is he's looked for all of the Argo profiles underneath the proposed cone of Tropical Storm Erin. So you're looking at the last week of Argo profiles that are caught within that cone. So going from yellow to blue, you can see how the water temperature increases dramatically over this period, or rather over this distance. When you're looking at the salinity, you can see the salinity decreases and then increases again. So the salinity decreases and then increases again. So there's a freshening of the water in this region. So between these two scenarios, we're looking at intensification of Tropical Storm Erin, which is being predicted within our latest forecast. So this is a real-time, right now use of Argo data to see what Tropical Storm Erin is probably going to do. So that was just a great slide to be able to introduce today. Okay, now I'm going to tell you a little bit about a cross-divisional hurricane study that we did here at AOML. And Jen, who I'm showing here, led the Argo effort on this particular project. So our physical oceanography, our hurricane research, and our ocean chemistry and ecosystem divisions were able to redirect a sail drone and a BGC Argo float into the path of an oncoming Hurricane Idalia. Our Argo float was put into rapid cycle mode, so that was able to report back to us every 18 hours. So this means that we were able to get pre and post storm data from underneath the track. And with the sail drone, we could get pre, post, and during storm data from the track line. So the video of the sail drone under the storm is available on YouTube, but I didn't share it with you this time. But go and have a look. It's really cool. So then Jen took the sail drone and the BGC data and she overlaid it over the satellite imagery. So what you're looking at here is sea level anomaly, sea surface salinity, and chlorophyll. The sail drone is in the star position and the Argo float is denoted by the square. And the track of the hurricane is this black line going through each of the satellite images. So first thing you notice is this beautiful loop stream in signal, the loop current signal coming through, and a nice cyclonic eddy right underneath the hurricane track. And what we found during the hurricane is that the middle Mississippi River plume extension became entrained into this eddy. So between the cyclonic eddy upwelling and the Mississippi plume, we have a lowering in the salinity signal, surface signal, and an increase in the chlorophyll surface signal. In fact, the sail drone was able to detect an increase of chlorophyll of up to twofold increase in chlorophyll, let me get that right, and a 6% increase in oxygen. Looking at our Argo data, so between the hurricane-induced mixed layer depth deepening and the cyclonic eddy upwelling and the inclusion of the river plume, we ended up with a subsurface bloom following Idalia. So looking at the Argo data, looking at the nitrates, we could see a reduction in nitrate at depth and an increase in oxygen at depth from pre and post hurricane. And I'm leaving it there because Jen has a paper on this coming out. It's in review, so I don't want to steal any more thunder. Okay, now I'm going to show you, great, I've showed you all these things. I've showed you what the data are used for. Where can you find them? If you just want to see if there is an Argo float anywhere near your area of interest and you want to overlay it with satellite imagery or look at a forecast, our AOML PhD Ocean Viewer allows you to underlay many different layers. From here, you're looking at sea surface salinity. You can use temperature, you can use, at this time of year, temperature was all the same color, so I decided to go for salinity. But you could use any layer that we have available. Here we have the National Weather Service forecasts. I chose a day when we had all kinds of activity around the US. And then you can see all of the little Argo buoy positions. You can overlay drifters, you can overlay anything that AOML touches, you can see where it is. Another really great dashboard is the U.S.Argo website. They have a dashboard that allows you to select active, inactive floats, year of deployment, country that deployed it, ocean it's in. You can even select what telemetry the float is using. And then of course, what DAC, and it goes on and on and on. I couldn't fit it on the screen. But what you would do is, for example, you choose all the AOML floats. So these are the floats that we've processed here at AOML. And then you would click on, say, one of them in the Gulf, and you could click on the trajectory, and it would literally draw the trajectory for you so you can see exactly what that profile is, where that float has been. Now, if you wanted to look at subsurface data, you might have to wait just a moment on our side, because AOML, here at AOML, we're working on a visualization project where we will have, for all of our AOML owned and deployed floats, not all of the U.S.Argo DAC floats, but our AOML owned and deployed floats, we're planning to set up a website where you can see the trajectory of each of the floats and a profile. Right now, you're looking at dissolved oxygen with dissolved oxygen on the x-axis and pressure on the y-axis. You can see every single profile in the history of the float. We're hoping to make, at the moment these are static, we're hoping to make them interactive, where you'd actually be able to go and just select one single profile. But here you can see exactly what the conditions were like at each point on this map. And the other thing that we're adding, and this is thanks to Hui for giving us this idea, because I think this is just such a super, super quality control plot for anyone that needs to look at data. What you're looking at here is the status of the data, the quality control of the data with depth on the y-axis and then the cycle number on the x-axis for dissolved oxygen well, this is adjusted mode dissolved oxygen, if anyone's wondering what the adjusted is. It's just versus real-time adjusted delayed mode. This is the adjusted version. And here you can see that within the high resolution data, all the way down through the low resolution data, all of these data are quality control 0.1, so QC1. And if you're wondering what this little zip over here is, that is when a float went over some topography and couldn't reach its maximum depth. So it stopped, it parked itself, and then the next profile it could go further. So it detected ground and didn't go over it. And that's really nice to see in a plot like this. Maybe I spend too much time looking at Argo data. And the reason we're not going to be doing that visualization, that level of visualization for all of the U.S.Argo Data Assembly Center datasets is because every float deployer has their own system. So a lot of what you'll see on our website in the next couple of months we're emulating what HUI does. So I'm not going to show you all of that, but if you would like to go and have a look at the HUI site, you will see all of their floats in exactly the same format. Scripps does the same thing. You can go and click on their floats and have a look at their profile data. Same with University of Washington. And that's it. So before I end, I just wanted to point out the partnerships that we have within the U.S.Argo program, specifically with the U.S.Argo DAC, because we work with everyone within the program, is phenomenal. We are constantly meeting with our collaborators. We have meetings monthly with every one of our float deployers. So we have one-on-one meetings with our float deployers every month, so we can really dive into any deployer-specific data issues that either we or they are having. We have bi-monthly what I call U.S.Argo DAC client meetings, where any of the folks that you're looking at with all these logos on the screen can come and join us and give them updates on any changes, big changes we've made to the code or to the DAC or to protocols. So every 2 months, we cover everything that's new that's happened in the DAC. We are currently working on a new data format called JSON data format. And so we're developing a new decoder. So 3 groups are working on the code development right now, 3. So PMEL, PMEL, Scripps, HUI, and us. We're all working on decoders to decode this new JSON format so that we can ingest it into our systems. But we meet as a team every 2 weeks. So anybody that's interested in the Argo JSON format data are invited, including private sector, are invited to our meetings to make sure that the data flow from instrument manufacturer all the way through to the GDACs is consistent and understood by all. So we have a lot of meetings. My DAC team hates me because all we do is meet, but this is why we have so many people that we work with, and I wanted to bombard you with just the depth of experience we have within the U.S.Argo program. And with that, I will take questions. Oh, by the way, there's the monthly report link, just in case you didn't get it before.